Bandwidth and wavefront are important concepts for the efficiency of storage in the finite element process. We're going to show how that concept ties into the factorization process. We'll do a floating operation count and talk a little bit about optimizing the situation. Then we'll discuss Wavefront as invented by Irons and Meloche and compare some computer costs on one particular code, then end with a problem session. Our discussion of bandwidth and wavefront will be rather fundamental. I'd like to get some simple concepts across. So I won't get into algorithm development such as Cuthell-McKee and all these methods, but let's understand the meaning of bandwidth and wavefront. First of all, these are actually storage optimization ideas more than anything. They both are used most often in conjunction with Gauss elimination type solvers. On mainframe computers where there is a charging algorithm for the customer, you find that the floating point operation usage will cost about a third of the total. And on the other hand, the occupancy of the high-speed storage costs about 2/3. So where there is accurate bookkeeping, you find that storage is actually more important than the floating point operations. So one lesson to be learned there would be that we should work harder on storage than on the solvers, and I think that's not generally appreciated. Also, the story is muddled a little bit more when you have workstation installations where you have a dedicated machine to your use, and then I guess the way that these costs enter could be modified. Generally speaking, finite element matrices are sparse, and that means, as in the example on the left here, you have scattered non-zero terms throughout the matrix, and many systems initially start out in this manner. Electrical networks, for instance, often involve interconnections between many grid points in a total grid and might look like this figure at the outset. There are other systems that have some connection topological features that would perhaps cause this kind of a matrix called a skyline matrix. And the reason that it's called that is it looks a little bit like London skyline here you see with chimneys on it. So you can imagine what this is like. We'll put a little smoke coming out here. Another kind of topology is the strictly banded system where there are zeros outside a certain region. And by leaving these areas blank, I imply that those are zero terms. There are times when each of these can be exploited in different ways, but we're primarily interested in banded ideas in this lecture. Let's discuss the terms bandwidth and semi-bandwidth. Now we'll do this in the context of real symmetric matrices. Here is a matrix of size n, that is n equations, and it has non-zero terms lying in a band that's marked by these red lines. The word bandwidth means the total width from side to side of the non-zero set of terms. The word semi-bandwidth means the set of terms, the width of the set of terms, including the diagonal term out to the edge of the banded region. We give that the symbol B. Now we can calculate B below here with this equation. The major feature here is that the difference in nodal numbering within an element, D, has to be considered for every element in the assembly. And when you find the worst such element that gives the largest D, then that dominates the band. Then you multiply by the number of degrees of freedom per node And in total, then, you will have the number of physical terms in the semi-bandwidth. To the side, I'm going to sketch the element that has the greatest nodal numbering difference. For instance, it might have nodes 2, 7, 13, and 22. And you can see that the biggest difference would be 20. In other words, D equals 20. And then that would go into this formula. And you add the 1 to account for the diagonal. Now the paradoxical thing is that although there's a clear distinction between the words technically, in standard usage, everyone, including myself and the code developers, will use the word bandwidth to mean semi-bandwidth on these symmetric matrix problems. And so the viewer must be aware that I will be using the word bandwidth from now on when I really mean semi-bandwidth. When you run an example on a computer finite element program, it will report out the bandwidth, and it really is the semi-bandwidth. Now that actually doesn't cause a problem in practice. Many matrix operations affect the character of the matrix involved. For instance, inversion and transposition. Inversion will take a sparse matrix and then turn it into one that is fully populated. So we might have the same worry about this process of factorization. If we had initially a banded matrix, what will happen after we factorize it? Will it become fully populated? Will we preserve the band? What if it's a skyline matrix? Will we preserve the skyline? The answer is fairly straightforward, it turns out. And basically, factorization does not spoil the bandwidth. It does one minor complicating thing, though, in that if you have a skyline type of matrix as sketched on the left here, that after that matrix is triangularly factorized, you do fill in the smokestacks that originally were in the physical matrix, so that the decomposed lower unit matrix shown here will in fact have these new terms coming in. And we can show that. Let's prove that triangular factorization does not destroy the bandwidth. I'm going to do the argument for a strictly banded matrix, but the same logic holds for the skyline matrix. Here's a banded matrix on the left, and I'm interested in what happens to that as it is decomposed and as it turns into this lower unit matrix on the right. And the real question is whether this dashed line that corresponds to the lower boundary of the band in the stiffness matrix will also carry over into the decomposed matrix. Well, we can concentrate on one row here and prove our point. We'll do the case of the first column in that row, the second, and then a general point in that column. Now, to show that the first term is 0, that lies in what we called region 2 of our decomposition. The matrix is decomposed according to this law, and you get Li1 is Ki1 divided by the diagonal term. Now, since you're below the band in the stiffness matrix, then whatever Li1 term is here, it's related to the Ki1 term here, and that is 0. So we've already shown then that the first term in L has to be 0. Then the second term would involve the region number 4 that we spoke about, and this time you're going to have a term Kij, where j is 2, and you're going to find that the K term is 0 because it lies below the band, which is over here. And then there's a sum, which is degenerate, involving only one term, which involves the Li1 term, which we've already shown to be 0. So this will vanish. So the second term in L is 0. Then if you go to the general relation here for a general term along that row, you find that there is a sum involving the Lik, and k takes values from the left boundary up to the term next to which you're considering, and those previous terms were all 0. And so there's a kind of a cumulative effect where you're accumulating zeros in your multiplication up to your current term, and then this entire sum is 0 for that general Lij term, provided you lie below the band of the stiffness matrix. So that's a little proof then that this now becomes a solid line here where once was a dashed line, and we will not have non-zero terms until we reach the band, and that bandwidth is the same as in the physical stiffness matrix. Well, finding that the bandedness is preserved under the triangular factorization is a great help, because now we don't have to store those terms. But a second feature is that you don't have to do trivial arithmetic multiplications on those terms either. So let's evaluate floating point operations now, and presume that we will not carry out multiplications involving 0 terms. Now, the most important operation that we did was the calculation of the Lij term in what we call the fourth region here, and of course that dominates by orders of magnitude in importance what happens in these vector-like calculations down the diagonal and down the first column. There are as many terms here to be calculated as there are terms in the matrix times the width of the band, because you're calculating these terms across the band now of the factorized matrix, which is b in width. So there are exactly nb terms there. Well, close to nb. Then in the sum that's being done here, we showed previously that when you were working from the first column in this particular last term, that it was a 0 term, and it wasn't until you hit the band, until k hits a column number appropriate to penetrating the band of the original stiffness matrix, that you start getting non-zero terms. So let me call this K0 or something. And then you'll find that there are only B such terms remaining in this summation. So in fact, the number of floating point operations that we have to do is on the order of nb squared. And this replaces the earlier idea for a full matrix that the Gauss elimination required n cubed operations. We see here that if anything, the bandwidth is more important than the number of equations. Now, that was the important calculation because the decomposition is the most expensive part of the solver. But let's also look at the forward solution and the back substitution. On the forward solution, we have n unknown intermediate vector terms, and then this set of terms here only needs to be performed again for the number of columns in which you are actually in the band of non-zero terms. And so again, we are summing not from 1 to I minus 1, but something like a K0. And in fact, there are only B such terms involved. So we get a number of floating point operations on the order of NB, which would be substantially less than the NB squared for the decomposition phase. And back substitution turns out very similar. There are only n terms of the displacement field that you're finding. And again, this time, you're only going to sum over the band in this operation, and there are only B products again. So we again get NB floating point operations. When you add together the decomposition, the forward, and the back substitution, that's common in linear static analysis, the number of floating point operations is proportional to a constant times NB squared and another constant times NB. Now you can essentially neglect the latter term and see this former one only. Some of the computer programs that report to the user on the CPU time required concentrate on this term and don't bother to even report the second term. So people are consistent in realizing that that's not a very important term at the back. Let's do a problem where we show the effect of nodal numbering on the bandwidth. We'll take the same physical problem and we'll number it two different ways. Here's the structure, which is a 3-element assembly of plane stress quadrilaterals. There are 2 degrees of freedom per node. I've done an unfortunate job of numbering these nodes in the first case by numbering through the thick dimension as shown. 1, 2, 3, and 4 at the top, 5, 6, 7, and 8 at the bottom. I'm going to use something called compact notation here, and this makes use of the node numbering as the only bookkeeping tool for connectivity. And the reason is that all the degrees of freedom at a given node play the same role. So therefore, all the connectivity information really is carried by the node numbering. As a result, I can show an 8x8 matrix and carry all of this information. You should interpret these terms in the matrix, these Kij, as a kind of element stiffness based on the numbering of the nodes. So Kij, the I and J would be nodal numbers. And then the little non-zero entries shown in here will actually be little 2x2 matrices. Well, let's start filling some terms in. For instance, for node 1, it's connected not only to itself, but to nodes 2, 5, and 6. And so I get the non-zero terms K11, K12, K15, and K16. Likewise, the second node is connected to nodes 1, 2, 3, 5, 6, and 7, which I'll outline here. Now you can continue on and fill in the rest of the non-zero terms and then outline the band with the red lines shown. The zeros are just entered as an afterthought where there are no non-zero terms. We see that the semi-bandwidth is 6 in this problem. We could also have gotten that result algebraically just by doing the equation that the semi-bandwidth is D plus 1, where D is the largest difference in nodal numbering. And in each of the elements you can see that D is 5. D is 5 in the first element, 6 minus 1. D is 5 in the second element. And D is 5 in the third element, just by chance because of the repetitive numbering scheme. And so our bandwidth will turn out to be 5 plus 1, which is 6. And we get the same result as before. Now let's look at a second nodal numbering scheme, and it really is the optimum one in this problem. Here we would number what I might call through the thin direction of the problem, numbering 1 and 2 and 3 and 4 and so on. So really there is a progression then of this numbering pattern from left to right, almost in a wave-like pattern. Now we reserve that terminology really for the Wavefront method, but it does have sort of common features in that sense. Again, we're going to use compact notation, so we'll only keep track of the nodal numbers themselves. Again, I will use an 8x8 matrix to characterize this two-dimensional problem. The node number 1 will connect nodes 1, 2, 3, and 4, and so I'll put those non-zero terms here. Node 2 will likewise connect 1, 2, 3, and 4. 3 will have a little broader range, 1, 3, 5, 2, 4, 6. It's completely 1 through 6. And let's go to 5 as a final example here. We'll connect 3, 5, 7, 4, 6, 8. So that's really 3, 4, 5, 6, 7, and 8. And we can finally bound the non-zero terms with the red lines and get a semi-bandwidth here of 4. Now we'll use the symbol B equals 4. Had we used the equation of bandwidth was the greatest difference plus 1, what would we have gotten? We would have, in the first element, had a difference of 3. In the second element, a difference of 3. The third element, a difference of 3. And so we would have obtained this number then, 3 plus 1 equals 4. And would have gotten the same bandwidth. Now, by now I am using the terms bandwidth and semi-bandwidth interchangeably, and don't be frightened by that. It's really, we always mean really the semi-bandwidth when we say that. Now, had I calculated these using detailed notation, there would have been a factor of 2, and rather than numbers of 6 and 4, respectively, we would have had 12 and 8 for our bandwidth, had we put them in detailed notation. Well, we've seen that by resequencing the nodal numbers, we've reduced the bandwidth of our problem. This would lower the storage requirements proportionately from 6 to 4, which would be quite a reduction in storage. It also would reduce the CPU time required. The CPU time was given by this formula, the number of equations times the bandwidth squared. And because our two problems had the same number of equations, we can compare the ratio of CPU time to be 4 squared over 6 squared. And that number is 0.44. So we now have less than half the CPU time required in the resequenced problem. Now, actually, you wouldn't achieve that reduction in CPU time on such a small problem because there are a lot of overhead items such as reading the data and assembling the matrices that would not let the CPU time be dominated by the decomposition. But this is kind of a upper limit on the obtainable number, then you would approach that for larger problems. Wavefront optimization is a little different approach to the idea of storage and CPU optimization. Irons and Meloche independently came up with this idea many years ago. You still are doing a Gauss elimination in a preferred order. This time, though, you're basing it more on element topology and numbering rather than nodal numbering. Wavefront methods are really good for computers that have dynamic storage allocation, and by that I mean the amount of storage allocated to the user can change in time. This would be often true on mainframe computers with time sharing. Let me give you the idea, and some of this, explanation that I'm giving has come from a document originally written by Structural Dynamics Research Corporation in support of the code Superb. I found it to be one of the more useful explanations of the wavefront scheme. Let's suppose we have this body here, and I show what would be a triangular element in the lower right, numbered number 1, and then a quadrilateral element, number 2. Number 1, if it were to be first assembled on an element-by-element basis, would involve nodes 1, 2, and 4. And so I show the red triangle occupying those locations. After you had assembled those equations, then you would proceed to element number 2, which would bring in terms involving nodes 1, 2, 5, and 6. And I show those in green over here. Now, this assembly of the stiffness has reached a point where we actually have fully summed all of the terms that will ever accumulate on grid point number 1. Therefore, it would be possible in the real-time solution to use your Gauss elimination to eliminate the variables associated with the node U1. So those could be removed in terms of the remaining nodes. Then as you progress around this body, you would continue to do that. You would eliminate any nodal degrees of freedom that were fully summed and move them out of high-speed storage. The interesting thing about this wavefront scheme is that it depends on the element numbering. So I'll illustrate that with the sample problem. Let's take this 3-element structure here and number it first in a bad way, numbering element 1 and then 2 and then 3. This definitely violates that feeling of a wave passing through a structure through the thin direction, and is sort of a jumping ahead and crawling back and so on. And it will turn out to be not optimum. When you form the element stiffnesses for element 1, you have these active nodes, 1, 2, 3, and 8. And when you've finished working on this element, you actually have fully summed all the stiffnesses that will ever appear for nodes 1 and 8, and those can then be dropped. And so you come down here, drop those. Then when you move over to element 2 on the far side here, you'll bring in stiffnesses 4, 6, 5, and 7, and that will give you a total of 6 active nodes that are being considered. But when you've finished with this element, you will never have any more terms on 4 and 6, and those are said to be fully summed, and you can remove those in terms of other degrees of freedom. Then lastly, you do the central node number 3, and at that point you have left 2, 3, 5, and 7. You solve those remaining equations, and then you are done with the problem because all of those are fully summed. The thing to watch is this central column, which is the active number of nodes, and given in this compact notation, we would say that the maximum wavefront is 6 nodes involved, and then if you had a dynamic allocation of storage, you would have been occupying an root mean square wavefront of 4.76 nodes. Now let's do a second numbering of the elements in our problem. This time we'll number more logically from left to right with elements 1, 2, and 3, thereby getting a little more of a natural wavefront progression through the problem. When we activate element 1, we will bring in the nodes 1, 2, 3, and 8. But when we're finished with that element, we will have completely summed nodes 1 and 8. Then when we activate the second element, we will have to add nodes 5 and 7. When we're done, we'll deactivate 2 and 3. And then the final element brings in nodes 4 and 6, and of course then when we're done we put everything to rest. This gives us a maximum wavefront of 4 and an RMS wavefront of 4. So we have decreased the storage requirements in the problem by this renumbering of elements in the ratio of 4 to 4.76. So it's something on the order of a 20% decrease in storage requirements. Zienkiewicz, in his textbooks, has given an example of the way that computer costs change as you go from 1 to 2 to 3 dimensions. And I think it's an excellent example. It's a little bit of a scare story and will almost overemphasize the point, but I like it. You should see this once in your life. We're going to compare the CPU costs for a one-dimensional problem at a certain accuracy level, and then a two-dimensional problem at the same accuracy level, and finally a three-dimensional problem. Now, by that I mean that as you go to 3 dimensions with a body like, for instance, the human head, which one time I was studying, you have to be as detailed in each of those dimensions typically as the others. And so when you go to higher dimensions, you don't necessarily use a cruder model in any of the coordinate directions. Now, we know that the CPU time goes like NB squared, and so we're going to have to look at what happens to the CPU time requirements as we go from one dimensional space to the next. Now, to make it more fun, assume that you're working for a company that owns a chain of Italian restaurants, and your boss comes in and says, Jones, we've got this problem with this clothesline, and we want you to do an analysis. And you say, okay, boss, it's a one-dimensional problem shown here. I'll consider 20 elements along this clothesline, and that'll mean 21 nodes, and I'll bring the answer in tomorrow. No problem. So you go off and you can calculate the CPU time requirements as proportional to the n, which is a number of equations. Now this is a one-dimensional problem, 1 degree of freedom per node. There are 21 nodes, so there are going to be 21 equations. And the bandwidth will be typically in the optimum numbering, going 1, 2, 3, and so on. We'll have a difference of only 1 plus 1 will give a bandwidth of 2. And so your computer time requirement will be proportional to a number 84. So you'll do the calculation and come back smiling, and the boss says, Jones, that was so good, I'm going to give you another problem, and this is the tablecloth problem. We have these checkered tablecloths, and the customers are pulling on the edges while they describe things, and I'm worried about the stress in the tablecloth. Get that to the same accuracy as the stresses in the clothesline. You say, okay, boss, no problem, I'll come back with the results tomorrow, I think. And you sit down and look at this one, and now you have a 20 by 20 pattern of elements in this two-dimensional problem. Now there are 2 degrees of freedom per node. The bandwidth is getting a little tougher because you don't get to come back in your numbering scheme until you've passed through one whole face. And so we can probably calculate the bandwidth off to the side here. Let's suppose we take the first little element and suppose its numbers had been 1 and 2, and then you'd come back with number 22 and 23. It will turn out the difference is 22 in that element, which is characteristic of the whole problem. And so the bandwidth, in fact, with 2 degrees of freedom per node in detailed notation is 46. Now the number of equations here will be the number of nodes, which is 21 squared times 2, because there are 2 degrees of freedom per node, or 882. And when you multiply that out, now you see that your time requirement is on the order, or at least proportional to a number of some 1,800,000. So it's jumped way up. So finally your boss comes to you and said, Jones, we've got this enormous block of mozzarella cheese that we've got to model. It's getting pretty tough. We've got to figure a way to beat this problem. He says, model that mozzarella cheese with a 20 by 20 by 20 set of elements. Similar accuracy as you had in your line and your tablecloth problem. And you say, yes, sir, boss, I'll be back tomorrow. So this time you go out, 20 by 20 by 20. And you know, when you count the degrees of freedom involved now are 21 cubed times 3, which turns out to be 27,000 equations. The bandwidth this time is really pretty tough, because numbering across the front face of this, you won't get back to your starting element until much, much later. And when you do, you can figure that bandwidth out as exactly 1,392. And this time your constant of proportionality here is 5 times 10 to the 10th. So in this case, I think the equation solver would start to dominate. The constants that we have developed for those 3 problems went as 10 to the 2nd, 10 to the 6th, and 10 to the 10th. And so the problem size was actually jumping in terms of CPU time by 10,000 for each jump in dimension. It sounds hopeless, but actually you see most solvers nowadays can handle up to 50 to 80,000 degrees of freedom without breaking a sweat. And so really we're still kind of down in the small problem size, especially at the lower end, the line end. And what we've done then finally is reached a medium size to large size problem at the end. So this fearsome growth in size of the problem in terms of CPU time isn't quite as bad as it looks. Classically, people have worried, though, whether you should follow this kind of logic and really use that many simple elements. In current times, there has been more of an emphasis on using fewer, more complicated elements, such as isoparametric elements with perhaps higher degree shape functions involved. So you might have mid-side nodes. In any event, the bottom line is, before you promise to do solid problems with a lot of detail, be sure that you have the computer capacity to solve the problem. Another way to study computer costs would be to compare problems of different size lying in the same space. Now, the example I'm going to give here was originally documented in the McNeil-Schwindler-Nastran information. And again, using the idea that CPU time goes like NB squared, then this time we're going to find the way that bandwidth varies as the number of equations. So we'll be using the number of equations as the baseline reference. Now, in one dimension, if you consider these three models involving increasingly large numbers of nodes, then the bandwidth in this case stays constant. It would be 2 in